Good afternoon, everyone. I'm Krzysztof Kotowicz, and we're gonna talk about JavaScript crypto for the next 40 or so minutes. Like I said, I'm Krzysztof Kotowicz. I'm a web security researcher. I did some HTML5 research and some browser extensions research as well. I was a pen tester at Cure53 company, and this presentation mostly covers the research that I did during that time. Now I am an information security engineer at Google. Google is a search company. It's sort of like non-Chinese Baidu. So a necessary disclaimer, all that you hear is based on my opinions, not one of my companies. And there are no 0 days disclosed. So let's start maybe by asking you a question. Raise your hands who thinks that doing crypto in JavaScript is a good idea. I see like one pair of hands. Okay, who think it is a bad idea? Yeah, significantly more people. So it's actually a terrible idea, and you can even Google it. So when you start asking questions about JavaScript crypto, you really quickly come across these two blog posts. The first one by Tomasz Ptaczek from Matazano Security, entitled "JavaScript Cryptography Considered Harmful," and that is pretty much the essence of the blog post. And the second one is from Nate Lawson, entitled "Final Post on JavaScript Crypto." And those two researchers or people mention several arguments why doing crypto in JavaScript is pointless or even dangerous. And if we try to divide all those arguments, they all come up to a certain 3 buckets. The first one is that JavaScript cryptography is not needed, because if you have a web application which is delivered by the server to the client and the computation is done on the client, specifically crypto computation, first you need to have an implicit trust in a server that the JavaScript code that it delivers is not backdoored, right? And also you need an SSL or TLS channel to protect against tampering with the data by some man-in-the-middle attacker. So if you already have a secure channel of communication, why doing the computation over this, like on the client side, if you can do all the crypto server side? So this is one of the arguments. The second one is that it's dangerous. Doing crypto in JavaScript is dangerous, mostly because XSS is so hard to solve as a problem in JavaScript security. And the third argument is that it is actually hard. So it is not only dangerous and not needed, it is also hard, because JavaScript in itself doesn't give you a lot of sort of support for the type of operations that you need to do in order to do crypto. So obviously, JavaScript crypto is doomed to fail. So everyone read those blog posts, read other books on the subject, and so on and so on. And the developers stopped developing JavaScript crypto, and we all lived happily ever after, right? Well, not necessarily. As you can imagine, it's 2014, and we have multiple JavaScript crypto libraries of different kinds. There are multiple crypto primitives libraries, like, I know, AES library, like hashing libraries, and so on. There's asymmetric and symmetric encryption libraries. There's TLS implementation even. A few open PGP implementations in JavaScript, and a lot of user applications built upon those libraries. And also, as it is usually in a crypto world, there's a lot of custom crypto protocols delivered by some people who think that actually doing crypto protocol is a fun thing to do. So there's a lot of area to research, because nowadays in 2014 we have a lot of applications to actually look at. And by looking at those applications, we may discover problems that are not theoretical, like they used to be 5 years ago or 7 years ago, but the problems that the JavaScript libraries actually have, like the actual libraries do have vulnerabilities, and what kind of vulnerabilities are there? And it is an interesting area to research, so hence this talk. So my plan on trying to understand the current state of JavaScript cryptography was to first look at the code of those different software projects, to find the vulnerabilities in them, to try to understand the root cause of these vulnerabilities, because ultimately the root cause of the vulnerability is not the, say, stupid developer or whatever, and it's usually lies much deeper, like the real root cause, like maybe the language doesn't give you certain protections or the platform. So what I came to understand is that JavaScript cryptography, usually the vulnerabilities in the software can be classified into two buckets, or the root causes of those vulnerabilities. The first one are vulnerabilities arising from the lack of support in the JavaScript language for certain features, or the quirks of the language. And the second thing are issues caused by web platform flaws, or web platform insecurity, or the flaws of web platform, because we all know that the web is broken and probably will be broken for the next 10 years or so. But the most important part is that I tried not only to understand the state of JavaScript cryptography in isolation, I tried to also compare the issues that I've encountered to native crypto, or crypto done in other languages, like other projects, GNU-PG, GNU-TLS, you name it, OpenSSL, whatever, because there might be some similarities in the causes of those vulnerabilities, and well, I will try to demonstrate that along the talk. So the language issues. If you think that the language issues or language quirk don't really matter to cryptographic code because basically it's just math, I mean, how hard can it be? You probably are going to fail in making such an argument, and I can even repeat that, you are going to fail. So let's take a look at the language itself. JavaScript is a dynamic language, obviously. It's a language which is weakly typed. It has a pretty weird model of inheritance called prototypical inheritance. It is a language with an implicit global object, which is interesting in its own, and the parser is pretty forgiving. So the language itself can be pretty tricky. Like, I know some of you probably know this already, but you can code arbitrary JavaScript code by using just 6 characters. So this one is obviously alert one. And you can imagine that this kind of this comes from 3 issues, like implicit global object, the weak typing, and the forgiving parser as well, and the type coercion. So if you encounter or try to do any serious computation in that kind of language, you will probably face many problems. So what problems can you face in JavaScript when doing crypto? Well, obviously there's weak typing, so there's a lot of type conversion, type conversion going on. So if you, for example, compare true, Boolean true to like a true string, it's true, they are equal, but the false is not equal to false. Also, the minimum number in JavaScript is actually greater than the maximum number in JavaScript. Like this one is actually infinity, and this one is minus infinity for some reason. And while null is an object, it's not actually an object, so yeah. As a result, developers rarely use, like say, strong typing, or rarely check types of the variables in JavaScript. And there's multiple problems with arising from that as well, for the crypto especially. So let's take a look at CryptoCat. This is an encrypted chat application written only in JavaScript. So there was a famous vulnerability in CryptoCat, and there was an exploit. I don't think it was published, but the methodology of constructing such an exploit was published, and this was named CryptoCat. There was no logo for that vulnerability. It wasn't that times yet. CryptoCat tried to generate a private key, which is obviously, because you can derive everything from the comments. It's pretty long. It's 64 random bytes, and it uses the CryptoCat random string function. But if you take documentation of this function, it's actually 64. Yeah, it is 64 bytes long. But the character set of each byte is actually, when you take a look at those numbers here, it's actually only decimal digits. So as you can imagine, there's much less entropy from, like if you try to generate a 64 random bytes, you have over 500 bytes, bits of entropy. But if you reduce that to using only digits, well, the matters are much worse. So because of that and a few other flaws, the private keys generated by some versions of CryptoCat were brute forceable for certain types of attackers. And this was the case because CryptoCat didn't use types well enough. It assumed some things when the language didn't really warn him against it. The other thing is magic properties, again, CryptoCat. So it's a multi-party chat application. So in order to start an encrypted chat with someone, you first need to accept his public key and then generate a shared secret. And then encrypt your communication with using that shared secret. So this is the code when CryptoCat checks whenever sort of new users appear on a channel. So it checks whether you already have the public key for the sender, and if you don't, you accept the public key that was just sent, and you generate a shared secret. And later on, during the communication, if you want to decrypt a message from someone, well, you simply check whether you already have the shared secret for this person, and then check. The shared secret is actually two keys. It's a key for authentication for HMAC, and the key for decryption. So you first authenticate the message, and then you decrypt it. It all looks sane, but JavaScript is magic. So let's meet user proto. So _ proto is a special magic property of every JavaScript object. And in this particular case, the value of proto is an empty object, but empty object is a truthy value in JavaScript. So if you treat it as a Boolean, it's truth. As a result, the first check, public keys proto, actually let me go back the slide because that one is much clearer. So I register as a user proto. So CryptoCat's client of the victim checks whether he already has a key with me, but actually he thinks that he already has registered a key with me because public key proto is a truthy value. So this block never gets executed. So as a result, the shared secret is never generated at all. And then I send an encrypted message to him, and he checks whether he has a shared secret with me. Again, I'm proto, so yes, this block will get executed. But actually, if you try to access the properties of the proto object, it's just an empty object. So this code will throw an error. So as a result, whenever someone named proto joined the multi-party chat, he broke the chat for everyone else. They couldn't communicate with each other. So again, JavaScript magic. But this is not unique to JavaScript at all. That's not the case. I mean, magic properties are present in a lot of, say, scripting or dynamic languages, in Python as well. So there was, for example, the large magic attribute or magic property, which can be sometimes used to alter the logic of the application as well. Silent errors. So if you create an array in JavaScript and try to access an index which is not present, it will return undefined. It's way better than C in that respect, in something written in C, but still, there's no error being thrown that you're trying to access something that you haven't, say, allocated memory for. And this is a silent error, and that's pretty common in JavaScript. Let's combine that with the other thing, which is completely different. Well, you have this thing called Unicode, and JavaScript strings are actually Unicode, so every character is not an ASCII value or something which character code is less than 256. It's actually like every character can be a Unicode code point. So there's very often JavaScript developers use this function to check for a value of a certain character within a string. And the problem is that if you supply a Unicode string there, the result of that is more than a byte value. So it's more than 256. And there's a lot of attacks with Unicode and JavaScript. This is what I consider the best presentation on this subject. So actually, but it doesn't matter to crypto? Yeah, it does. You can combine the two facts and do something called a 16 Stoneman attack. This is obviously some Unicode code point as well. So this is an attack discovered by Daniel Bleichenbacher, and it's an attack against an AES library written in JavaScript, obviously. And this attack allows the attacker to get the knowledge of the secret key, of the key used to encrypt and decrypt the messages by simply encrypting something with an unknown key and then decrypting the result back. Let's look why is that happening. But first we need to learn a little bit about AES. So AES, in this case it's AES 128. It's a block cipher, and it's a block cipher constructed of multiple rounds. So the encryption looks like that. First you have a plain text. Let's say it's a single block, so it's 16 bytes. Then you have a key scheduling mechanism. So you XOR the plain text with the round key. And then there's a few rounds of like sequential operations. And this operation, sub-bytes operation, being done n times, is actually combining the input. The input will be called a state. So within AES block cipher, you have a state, 16-byte state, which changes along the algorithm, and the resulting state is a ciphertext. So this particular function gets as an input the state, the current state of the cipher, and the S-box. This is a constant value, the 256 bytes of a constant value like defined in the algorithm. And this one is the inverse box, but we'll talk about it later. So what will happen if you try to encrypt 16 character string, which is what this library used, but instead of putting like the byte values there, you put in Unicode values? Well, to the sub-bytes function, you get a state which is 16 characters, but those are obviously more than, each of them is more than 256. So then the sub-bytes function is actually a mapping function. So it modifies the state by looking at the entry for this constant X-box array and like producing the value which is it's hard to describe in a few words, but basically having an input, this is a constant input, and this is the state. It alters the state by looking up values in the S-box array. But in this particular case, the S-box array has only 256 bytes. So the state here is more than 256. So as a result, you modified the state to being 16 undefined values. And yeah, you basically kind of altered the first round of the AES cipher, which is kind of bad enough, but there's more. So another function being called in each of the rounds of the AES key is the mixed column step. And the mixed column step actually silently recovers the state for you. So you have this poisonous undefined values. And then the mixed column step, without going into many details, it performs a lot of XOR operations. And one of the operations in this case is basically undefined, XOR 0, which obviously for JavaScript is 0, because why wouldn't be? So by calling this function, you sort of recover the state to being safe integers instead of those weird undefineds, which might trip the cipher further on. So after the first round, or just before the last step of the first round, no matter what the plaintext was, if it was this modified Unicode thing, you change the state of the AES cipher to being 00000, 16 bytes. And then there's the decryption. So the decryption is obviously being done in reverse. So first you have a few rounds of decrypting thing, and then at the last round you get those zeros back. And let's see what happens then. So there's an inverse subbytes function, which is very similar to the subbytes function. It's just that the constant array is actually an inverse of a certain kind of the S-box array used during encryption. But this time we have 16 0 bytes. So every item in the state will become the first entry in the inverse S-box array, which happens to be 52 hexadecimal. So as a result, if you encrypt something Unicode-ish with the key that you don't know, and then decrypt the result with the same unknown key, you reach back to at the last step, you have 16 constant value or known values to you. And then there's the last step, XORing with the round key for this particular round. So as a result, the plaintext that you receive is actually XOR of the key with this 1652 bytes. So this is a beautiful attack showing how weak typing and type coercion done in JavaScript can actually result in having a really serious vulnerability. But again, this is not something unique to JavaScript. This is a vulnerability from this year, GNU TLS, and it allows to bypass the certificate validation. What happens? So there's a checkIfCA function, which is basically being called whenever you need to validate whether the certificate was issued by a trusted issuer. And it obviously returns true or false, though actually it returns an integer. And in C you don't have exceptions. So usually when you have an error signal, you return a negative value. So because of that, whenever the attacker was able to trigger an error condition in this function, and it is pretty easy, you send an invalid certificate in a certain way. The caller of this function, which performed the whole chain of certificate validation, it compared the result value from this function from 0, because obviously, if it's 0, it's not a CA, the certificate is not trusted, so abort the whole chain. And if it's not 0, well, obviously, the certificate is fine, so just accept the connection. And yeah, so -1 or whatever error message value was there, get passed through this block. This block was never executed, and you were allowed to set up a man-in-the-middle attack through that. I would argue that language issues that I have just described, they are not unique to JavaScript at all, even in crypto. And you can overcome them. You can overcome them by, for example, using the ECMAScript 5 strict mode. You can use type enforcing by using certain JavaScript compilers which do checking during the compilation step of building the software. And obviously the development practices are pretty important in avoiding this types of vulnerabilities. So you have code reviews, continuous integration, unit testing, and whatsoever, like the real sane development practices that are true for whatever kind of software you do. About the far more worse issues with JavaScript crypto are web platform issues. So the thing is the JavaScript code doesn't execute in a sort of an entity which is unknown. It's actually a very concrete entity. It runs in the JavaScript engine, and there are a few of those. It runs in an execution environment. For example, it can run in a browser process, or it can run on a server, like Node.js, for example. The code has access to different APIs, like, say, DOM when you run in a browser, or Web Crypto for some browsers, or browser extension API, or whatever. Like Node.js has, for example, bindings for doing socket connections. And even running in this environment can be different because you have different restrictions placed upon the code. The most famous one in web is same origin policy, but there are multiple other policies that might affect what your code can or cannot do, like content security policy, iframe sandbox, extension security policies, and so on and so on. And vulnerabilities arising from those issues are much more important in crypto. Obviously, XSS is just a lame example here, because we all know XSS is not going to be solved as a problem all over the board. You need to solve the problem for yourself, usually, for your application. But what I would argue is that you need to look at cross-site scripting as an equivalent of remote code execution, especially in crypto libraries, because XSS can basically bypass any sort of security guarantees that your JS code has within the same origin. So, for example, you can replace a random number generator, exfiltrate the key, or like you're almost limitless in that area. And are there XSS vulnerabilities in crypto libraries or crypto applications? Obviously, yes, there are. Like the most famous one. Hello, Mario. This is you. Mavelope, this was an OpenPGP implementation in JavaScript. And it was really combined with the Gmail interface. Gmail is a webmail from Google. Whenever you test something like this, the most obvious thing to do is check for DOM XSSs. So what you do is you fetch your victim's public key, which is public by definition, and you encrypt the message to this victim. And the message says, IMG owner or whatever, like standard DOM XSS payload. And obviously this extension performed the whole decryption, asking for a passphrase, and in the end, after the decryption, it inserted the text back into Gmail user interface, obviously lacking any sort of filtering, escaping, or just used inner HTML and be done with it, because we need HTML emails. Everyone wants them, right? So obviously, via using this crypto application written in JavaScript, you could execute arbitrary code in a Gmail interface, which is already pretty bad, but not bad enough. Because you don't still have access to the private keys, right? So let's take a look at CryptoCat back. It had a similar vulnerability. It didn't filter the username or conversation name. So you could create a second CryptoCat client, just remove the validation being done totally in JavaScript when entering values in the input field. So you put an XSS payloads within your username and try to chat with someone using CryptoCat as well. And obviously, inner HTML, XSS pops up, done. So CryptoCat had two versions at the time. It was used as a Chrome extension, and in that case, we were already protected by content security policy enforcements. So we couldn't execute any JavaScript code. We could only spoof the user interface, which is bad, but then again, pretty limited. But in Firefox, the matters are pretty worse, because in Firefox, you not only get an XSS within the add-on code, you also can execute arbitrary code on a machine as well, because Firefox gives such an API available to JavaScript in the Firefox add-on. So this means that basically through CryptoCat I can install malware on your computer. Done. Again, RCE is not unique to JavaScript or web crypto. RCE vulnerabilities are still present. They are pretty rare, I agree, but they are still present in current native, widely trusted applications. Like, for example, GNU-TLS. You could pwn the client of GNU-TLS, but like server could pwn the client by triggering a buffer overflow. And this is also a vulnerability from this year. Another type of issues are timing side channels. So there are certain functions in crypto protocols that you need to execute without, they need to execute without producing any sort of time side channel, especially timing side channels. Like for any combinations of inputs, the code should run in a constant amount of time. And this is usually tricky to do. It is pretty tricky to do in JavaScript in general. But for example, this is an example from OpenPGP.js when it's decoded an RSA padding. This kind of padding in RSA needs to be executed constant time in order to avoid it's called Bleichenbacher attack. But this function obviously has multiple branches, so this code will only execute, which takes some time, when this condition is met. There's also a similar thing going on here, like return, there's an early exit. So this particular function is not constant time. And this is a problem for crypto. But again, this is not something unique to JavaScript or web crypto at all. We have timing side channels, and we have exploited timing side channels already in this example this year in Java, secure sockets extensions. So these kinds of issues are also present in other types of crypto environments, let's say. There's something more. Like we all probably remember Heartbleed. It was not even a crypto vulnerability. It was just I need to use the word, it was stupid, yeah. It was stupid lack of bounce checking. It just so happens that it was a lack of bounce checking in crypto software. And through that, the client could extract arbitrary, not really arbitrary, but a memory content of a server bypassing the, say, confidentiality promises of the TLS stack. Fortunately, this is JavaScript. We don't have buffer overflows here. Like, we are safe. We don't have those kind of problems. There's no way, right? Wrong. Well, you know, JavaScript it's not an abstract, cloudy thing. It's something that runs in an engine, and the engine has vulnerabilities in it. In this particular case, even this year, there were two vulnerabilities in different JavaScript engines, one used by Firefox and the other used by WebKit, Blink, or whatever. And these vulnerabilities allow the attacker, as you can see, by using a JavaScript payload. In this particular case, you just overwrote a getter for the byte length property of an RI buffer object and make it so it returns a pretty big value. And through that, the attacker was able to read and write arbitrary memory addresses. So no, we do have problems with memory safety when doing crypto in JavaScript. We need to take a look at browsers as an attack surface as well, because the attackers can target not your application, they can target your browser. And the browser is pretty large attack surface. It has an HTML parser, constantly changing. It has network stack. It finally has a JavaScript engine, also very dynamic. And the problem is that the attacker can trigger the JavaScript-based or HTML-based payload against the browser by simply enticing you to visit a URL. So what happens when the attacker actually executes or exploits a vulnerability in the browser? It depends on the browser. So in Firefox, for example, it's pretty much game over because the whole browser is a single process. In IE, there are multiple processes, and they are kind of sandbox, and there are also some exploit mitigations employed there. I need to say in Chrome, Chrome currently is the best one, in my opinion, when it comes to sandboxing things being run within the browser. Because in Chrome, you have a sandbox, like there's a clear separation. Every JavaScript is run actually in the renderer process. And there's separate renderer process more or less for every tab that you visit. And in order to exfiltrate, for example, secrets from that tab, you need not only to exploit the browser here, you need to escape the sandbox. And these are just, sandbox escapes are still present, but you need to have two vulnerabilities. I would argue that this is a malware problem. I mean, if you want to be so paranoid to try to protect against your JavaScript crypto application from the exploits targeted to the browser, it's similar if you tried to protect the native crypto applications from someone triggering a kernel exploit. And actually, yeah, this has been done. Like GNU-PG, even in their FAQ, they mentioned that GNU-PG has been bypassed by the Drug Enforcement Administration authorities by simply installing a keylogger on the victim's machine. So yeah, there was no crypto thingy. They just pwned the machine. And for JS crypto, your browser becomes your operating system. So whatever countermeasures you have in host security, you should have them in browser security as well in order to have comparable levels of safety. Unfortunately, these two environments, like the operating system programs or processes and web applications, have one really big difference. And the difference is in the application delivery phase. Because basically you don't install websites. In order to execute sort of arbitrary code within your, say, operating system or as a separate application, you need to basically download it somehow, verify it, and run it. There's a process doing that, and nobody does like constantly update their applications and downloading hundreds of software packages daily. But you do exactly that when browsing the web. You execute like hundreds of megabytes of code, arbitrary code, coming off through HTTP, HTTPS, whatever, from various origins. And yes, there can be an exploit in there somewhere, and you're very weak in trying to verify all that, right? So this code delivery and execution is pretty transparent for the end user. And the only thing that protects you is same origin policy, like that's ever helped anyone, at least in the crypto world. That's a very weak protection mechanism that you have. So is JS crypto actually doomed? Like, shall we never look at it? Because you create a perfect, access-free JS application. It's constant time, there's no side channels at all. You ensure that your server will never get compromised, and you also earn the trust of your users that you don't vector your code. You put this in a website, have perfect forward secrecy, the NSA never gets your keys, whatever, you serve it over HTTPS with absurdly large symmetric key size, and you're safe until anyone just triggers a browser exploit in a separate tab, right? Or finds the same origin policy bypass. So are we doomed? I would say maybe, but there's hope. Extensions can help you a lot, browser extensions. These are not plugins, these are just JavaScript applications as well. So you can have one for Firefox, you can have one for Safari, you can have one for Chrome or Chromium. And actually, it's a JavaScript application, so we can use the same JavaScript libraries within the context of the extension. But the difference is that the extensions run in a sort of isolated world. And you also need to install them. So this is a hopefully conscious decision by the user to install or upgrade the extension. With browser extensions, you get secure and signed code delivery from a lot of web stores, let's say. Well, unless you want to install the extensions manually by ignoring the warnings that the browsers give you. You have way better separation from other websites, so basically from other arbitrary code that can trigger exploit on your browser than just a thin layer of same origin policy. You get much smaller attack surface because basically you only care about your inputs to your application, and yeah, that's your attack surface here. And also in Chrome, you get, it's not perfect, but you get a process isolation. So you have a guarantee that your browser will run at least in a separate process, like an operating system level process. There are still open problems. For example, the timing side channels in JavaScript, even if your JavaScript code, looking at it, that has no side channels, your actual JavaScript engine, they are pretty aggressive in optimizing things because, you know, browser wars and whatnot. So they can optimize your code and make it non-constant time. So Eduardo Villanava gave a really beautiful example of how you can actually practically exploit those possibilities. We also don't have an mlock equivalent. Mlock protects secrets from being swapped out to disk. We don't have that in JavaScript, so your secrets can always end up at disk under memory stress. We don't yet have a secure store. We have to wait for Web Crypto to deliver it. There's a specification, but the implementation is, I would say, pretty slowly progressing. Also, there's, extension currently silently auto updates. So, you can download an extension, audit the code, but a month later it might be a different extension, and you don't get to agree to an upgrade. It's silently being done. And there's some quirks with process isolation, some certain situations under which you might end up sharing a process with someone. So the summary, JavaScript Crypto has similar problems to native crypto. The library quality is way better than it used to be. And actually, it's not the XSS which is the problem being mentioned. It's actually sort of pretty large attack surface coming from the browser. And you can solve the problems that the other researchers pointed out by multiple ways, mostly just being developing your software in a sane way or having code reviews, all these boring things which are actually essential, but nobody mentions it. So the platform issues are way more difficult to handle, but you can have relatively safe JavaScript cryptography when being run in a browser extension. And this is the end. If you have any questions, I would be very happy to address them. Thank you.